For this lesson, we will discuss optimization applications. Consider the following problem. A manufacturer produces gas grills that sell for $400 each. The total cost of producing X grills is approximated by the function here. What is the revenue function in this situation? What is the profit function in this situation? And find the number of grills should be made to guarantee maximum profit, and what profit will it be? So letter A, the revenue function is equal to the price, the selling price, times the number of grills sold. So that means R of X is equal to, our price is 400 times the number of grills. So X is the number of grills produced. So X is the number of grills produced. So revenue function is 400X. Next, what is the profit function? So the profit is equal to revenue minus the cost. So that means revenue function is 400X minus the cost function, that is 525,000 minus 30X minus 0.012X squared. And then you simplify this, we call the profit function P of X. So profit function P of X is equal to 400X. You distribute the negative sign to each term in the parentheses. So we have negative 525,000 plus 30X plus 0.012X squared. And then you combine similar terms and then arrange the degrees of the variable in decreasing order. So we have 0.012X squared plus 430X minus 525,000. This is your profit function in this situation. Next, we want to find the number of grills should be made to guarantee maximum profit. And then after that, we want to know what will the profit be. Now, to find the number of grills that should be made to guarantee a maximum profit, we need to maximize our profit. So that means we need to look at the profit function and find the critical number of the profit function. We can do that by differentiating P of X. So we need to find P prime of X. That's the derivative of our profit function. So the derivative of this is 0.024X. And the derivative of 430X is 430. And by the way, there is a typo in the equation here. This should be positive instead of negative. And then with that, this becomes positive. And this will now be negative. So that this becomes negative, and then here for the derivative, that becomes negative. So next is to find the critical number of the derivative of the profit function. We do that by equating this to 0. Then to solve for x, you transpose this term here to the other side of the equation. You get negative 0.024x equal to negative 430. Then divide both sides by negative 0.024, negative 0.024 to solve for x. So x therefore is equal to 17,916.666, which you could round it off to 17,917. Now next is to find the maximum profit. So to find the maximum profit, we're just going to plug in this value here, or this number here, to our profit function. So we will evaluate it at 7,917. So plug that into the equation here. You have negative 0.012, 17,917 squared plus 430 times 17,917 minus 525,000. And then plug that into your calculator. Plugging this into your calculator, you get 33,270,83.332. So that means 3,327,083. Another example. A disease has hit College Station, Texas. The percentage of the population infected T days after the disease has arrived is approximated by this function here. And this is for time T between 0 and 40. After how many days is the percentage of infected people a maximum? And what is the maximum percentage of the population infected? Now, before we proceed, let's just take note that we're given here a close interval. So if we're given a close interval to find the maximum, absolute maximum, we would need also to check at the endpoints of the interval. So the process here is the same as determining the absolute extrema on closed interval. We will begin by finding the critical number and finding the value that will make this, the derivative of this function, equal to 0. And then use that number and the endpoints of the interval to evaluate the function p of t, and then compare the resulting values. And then the highest value will give you the maximum. Okay, so now let's proceed to find the derivative of the function p prime of t. So find the derivative. Note that we have a t here and a function e, or exponential function, e to the negative t over 8. That means we are going to use product rule in this case. So we have t times 10t, so copy the factor, 10t times the derivative of e to the negative t over 8. So the derivative of e to the u is e to the u, so that's e to the negative t over 8, times the derivative of u, that's negative t over 8, with respect to t, plus, copy the other factor, e to the negative t over 8, times the derivative of 10t. And the derivative of 10t is 10. Then you simplify this, you have 10t times e to the negative t over 8 times the derivative of negative t over 8 is equal to negative 1/8 plus e to the negative t over 8 times 10. So we'll write 10 first. Next is to factor this out, since it would be easier to solve for t when we factor this out. So let's consider or look at each term and find the common factor. So note that each term contains 10 and e to the negative t over 8. So 10 times e to the negative t over 8 is a common factor. And then we're left with t and negative 1/8. So that gives you negative t over 8 plus, now this whole thing here is factored, so we're left with 1. So plus 1. And then you equate this to 0. Now, if this expression here is equal to 0, that means that either 10e to the negative t over 8 is equal to 0, or negative t over 8 plus 1 is equal to 0. Now, note that if you have exponential function, that function will never be 0. That will not cross your x-axis. So this means that this case here is not possible. Okay, so we only need to consider this part here. So we solve for t here. You can solve for t here by first transposing 1 to the other side of the equation. So you have negative t over 8 equal to negative 1. And then you multiply, so you only want t, so you multiply both sides by negative 8. So that 8 cancels out, and then negative times negative becomes positive. So we have positive t here. And that is equal to negative 1 times negative 8 is positive 8. And this t here is on the interval 0 to 40. So t is on the interval 0 to 40. And that's what we're interested at. So to find the time or the number of days such that the percentage of infected people is a maximum, we need to plug in this value of t here and the endpoints of the interval to the function p of t. Now the time that will give us the highest value is the time that gives the minimum, the absolute maximum. So p of t is equal to 10te to the negative t over 8. So we will evaluate this function at t equals 8. So that is 10 times 8 e to the negative 8 over 8. And that is just equal to 80 e to the negative 1. And then you plug this in using your calculator. You get 29.43. Now, next is p at 0. That is 10 times 0 e to the negative 0 over 8. This is equal to 0 because this is already equal to 0. And then we have p of 40. That's the other endpoint of the interval. That is 10 times 40 times e to the negative 40 over 8. this is equal to 400. E to the negative 40 divided by 8 is 5. And then let's plug this into your and this is equal to 2.7. Now the highest value is 29.43. This is the absolute maximum. Now since we want to find the time such that the number of days such that the percentage of infected people is a maximum, therefore we say that the answer is 8 days. So T is equal to 8 days. And for letter B, we want to find the maximum percentage of population infected. So since P of T is the percentage of population infected T days after the disease has arrived, that means that the maximum percentage of people infected is 29.43%. So this Y value here is the maximum percentage of people infected after the disease has arrived. A farmer has 1,200 meters of fencing and wants to enclose a rectangular field bordering a river with no fencing needed along the river. Let X represent the width of the field. Find an expression for the length of the field, the expression for the area of the field, the value of X leading to the maximum area, and find the maximum area. So these steps here outlines the process to find the maximum area. So first, let's try to illustrate the problem. Suppose this is the river and this is the area that you want to enclose using the fencing material available. Now in the problem here, the width is represented by X. So if that is X, this side is also X. And the length here can be written in terms of X. So if this is the river, we don't need any fencing on this side here. Now the fencing material is 1,200. And this will enclose your X. And then you have 2X here. This side here is X and this side here is also X. So that means 2X plus the length here. Now you can solve for length in terms of X. So you have 1,200 minus 2X. So L now is written in terms of X. Now to find the expression for the area of the field, so we know that the area is the area of a rectangle and that is length times width. Now our length is given by the expression here, that is 1,200 minus 2X. And the width is X. So the expression here is the expression for your area. And then we can distribute X to each term in the parentheses. We have 1,200X minus 2X squared. Now to find the value of X leading to the maximum area, we would need to find the critical number of the function here. So that is to first find the derivative of A and equate the derivative to 0. So A prime of X is equal to the derivative of 1,200X is 1,200 minus the derivative of 2X squared is 4X. Then you equate this to 0 and solve for X. So to solve for X here, we will transpose that on the other side of the equation. That becomes negative 1,200, and then divide both sides by negative 4. So negative 1,200 divided by negative 4 is 300. Now, to verify if 300 will really give us the maximum or the absolute maximum area, we will have to find the second derivative of the area and use the second derivative test. So you have a double prime of x is equal to, just take the derivative of this expression here. The derivative of 1,200 is 0, and the derivative of negative 4x is negative 4. Now in this case, regardless of what the value of x here, the second derivative is always less than 0. And if it's less than 0, the curve there is a maximum. The curve is concave downward, so that gives you a local maximum. So this x here would lead you to a maximum area. Now, so to find the maximum area, you're just going to plug in 300 to the equation for the area. The equation for the area is given by this. So you have 1,200 minus 2 times 300 times 300. Or you could plug it in by using this equation here. But this is easier if you don't use a calculator. 2 times 300 is 600. 1,200 minus 600 is 600. So again, 1,200 minus 600 times 300. So you have 600 times 300. And that gives you 180,000 square meters as the maximum area. An open box is to be made by cutting a square from each corner of a 3-foot by 8-foot piece of cardboard and folding up the sides. What size square should be cut from each corner in order to produce a box of maximum volume? Now, to solve this, let us first illustrate the problem. Take note that the unit here is in feet. So we will first need to convert it to inches. So you need to convert it to inches because if you're going to cut a square and you want to maximize the volume, you want the volume to be as small as possible. So you don't want to cut something in feet. You don't want to cut 1 foot in the cardboard to maximize your volume. So first, let us convert our units to inches. Now, 1 foot is 12 inches. So therefore, 3 feet times 12 is equal to 36 inches. So this one is 36 inches. And the other side, that length there, is 8 feet times 12. That's equal to 96 inches. So these are now in terms of inches. Now, if you want to maximize it, you want to cut maybe a small possible square on each corner. Now, this one here, you don't know yet still the dimension of the square. You just let that be equal to x. So each side of the square is x. Now to set up the equation for the length and the width, now if this is x here, and this is also x. And if the total length is 96, the length from this point here up to this point is equal to 96 minus 2x, because the total length is 96 and you want to cut x on this corner here and x on that corner. So that is equal to 96 minus 2x. And similarly, for the width, if the total width for the cardboard is 96 inches and you want to cut x inches here and also x inches here, the length from here to here is 36 minus 2x. Now in this problem, we want to find the maximum volume. You want to produce a box of maximum volume. That means you want to maximize the volume. So we go ahead and set up the equation for the volume. Volume is length times width times height. Now let's write the volume in terms of x. Your length in terms of x is 96 minus 2x times the width, which is 36 minus 2x. And the height is x inches. And then next is to find the critical number. So since we have a product here that is in terms of x and we have 3 factors, it is easier to compute for the derivative when you just multiply the x here to one of the factors here. So let's go ahead and write this as 96 minus 2x times 36x minus 2x squared. And after that, we take the derivative using the product rule. So using the product rule, you copy first one factor here, 96 minus 2x. And then you differentiate this factor here. The derivative of 36x is 36. And the derivative of negative 2x squared is minus 4x. Plus, copy the factor here. That's 36 minus 2x squared times the derivative of this factor here. The derivative of 96 is 0, and the derivative of negative 2x is negative 2. Then you simplify. So to simplify, you expand this using the FOIL method. 96 times 36 is 3,456. 96 times negative 4x is negative 384x. And 2x times negative 2x times 36 is negative 72x. And negative 2x times negative 4x is positive 8x squared. Minus 36x times negative 2 is negative 72x plus negative 2x squared times negative 2 is positive 4x squared. Then combine similar terms. 8x squared plus 4x squared is 12x squared. And then all those with x's, negative 384x minus 72x minus 72x. Using your calculator, that is equal to negative 528x. And then copy plus 3,456. Then you solve for the critical number by equating this last term or expression here to 0. So you get v prime of x, equate that to 0. So you have 12x squared minus 528x plus 3,456 equal to 0. Then you look for common factor. Now, if you try to divide each factor here by 12, you will see that each of these terms here is divisible by 12. So therefore, dividing 12 both sides of the equation will give you x squared minus 44x plus 288, and then you equate that to 0. Then you factor this expression. You have x minus 36 times x minus 8 equal to 0. Then for this to be 0, you have to equate each factor to 0, minus 36 equal to 0, or x minus 8 is equal to 0. So you have two values of x equals 36, or x is equal to 8. Now, to know which one gives you the maximum volume, you will need to find or use the second derivative test. So let's find the second derivative of the volume. The second derivative, so this is the first derivative of the volume. So take the derivative of the first derivative here. That's your second derivative. The derivative of 12x squared is 24x. The derivative of negative 528x is minus 528. Then you evaluate the second derivative at these values of x. So we have v double prime at 36, and the other one is v double prime at 8. So you evaluate this. So you have 24 times 36 minus 528. And then also 24 times 8 minus 528. Let's plug this into our calculator. So for this, you get positive 336. While if you plug in 8 to the second derivative, you get negative 336. Now, if the second derivative is positive, that's greater than 0, we have the concavity is concave upward. So this is a minimum. At the critical number, it's a minimum. Now, while if the second derivative is negative, that's less than 0, we have the concavity is concave downward. So we get there a maximum. Now, since we're interested for a maximum volume, we're interested for x that will give us a maximum volume, that means that x must be equal to 8 inches. So therefore, the dimension of the square that will give us the maximum volume is 8 by 8 inches.